Tonight, we are in for a real treat as Dave Buchla shares his latest adventures and insights with us. He was one of the club's founders, along with Bill Thomas and Vice President John Griffin. What year was that? Mid 2000s or something, right? It's been about 20 years. His dedication to education and community outreach has made a lasting impact on our club. He has an interest in all things astronomy, especially solar eclipses and auroras. 20 solar eclipses, 20 eclipses? 18, close. Well, that's it. That's just 18. Okay. We went with on a caravan with him to Idaho in 2017. It was a lot of fun. And he has been our speaker multiple times, employing a wide variety of genres, from the scientific to the historical and biographical, weaving them together with sky images, travelogue photographs, and tall tales from his worldwide travels. Is that a sentence or what? This is only the second time he's returned to Grass Valley as speaker since moving to Georgia in 2021. Now retired, he spent his working years in science and teaching. He worked for Sperry Gyroscope Company, where he taught radar to the military. After 9 years with Lawrence Livermore National Lab and 3 years with Science Applications, Dave taught electronics and physical science at Yuba College. He has authored and co-authored 11 textbooks, as well as a number of lab manuals for Pearson education. His topic tonight, this evening, is magnetic fields and the aurora. Welcome, Dave.
I just want to tell you how great two things are. Solar eclipses, everybody's got to have it on your bucket list to see a total eclipse at the site, at totality, at 100%. And secondly, put auroras on your bucket list. A great aurora is not quite up with solar eclipses, but it's close. The talk tonight, I have a table of contents here. I hope I didn't. Here we go. Oh, I could have on this one. Okay. Here's a couple of quotes I like. First one, not only does the Earth have a soul, but it's a magnetic one at that. William Gilbert, 1631, or 51, whatever that date is. I can't read the number, 31. And the other one, this is kind of important. I actually attended a lecture by Richard Feynman, and I don't think he made this quote at that point, but in his book he says, magnetism and electricity are not independent things. They should always be taken together as one complete independent field. And I'm going to emphasize that in particular, the relationship between electrical fields and magnetic fields. This is an outline of the talk. The first part before the break is going to be the magnetic field. Second part's the aurora. Magnetic fields include the fundamental forces, orbits and orbitals, and what's the difference, magnetic domains, the magnetic field. There's changes in the magnetic field and the correlation to oxygen. Some of this is maybe stuff you don't want to hear, but the second part over here, I won't read the rest of these to you. You can read them yourself if you like. Second part, I'm just going to go through the various parts of it, Aurora, and there'll be some slides that I think you'll enjoy. Hopefully you will. So the first part, we'll start with the magnetic field. Standard model of physics describes the universe in terms of 4 fundamental forces. Gravity is the attractive force between masses, and Einstein's relativity suggests that gravity is not a force, but bending to space-time. Newton thought of it as a force, by the way. The strong nuclear force holds the nucleus together. The weak nuclear force is responsible for radioactive decay and is responsible for beta decay when a neutron can transform into a proton and emit an electron. So one of the things that I just said was electricity and magnetism, which holds the universe together, is the principal thing we want to talk about with respect to auroras and that power auroras. So what I want to do is do a quick demonstration of that relationship. So if we can have a front room light, I have, I called it my F-14 binoculars, but it's two pipes, PVC pipe, a copper pipe, and a very strong magnet. This magnet is capable of messing up heart monitors and anything like that. So I'm not going to pass it around. But I just wanted to prove to you that magnets are not attracted to copper. They're not attracted to PVC pipes. You already knew that. But let's have a race. Todd's going to be my assistant. I'm going to drop it in the pipe, which is, I'm not doing a magic trick, but it may look that way. But here it comes. Don't drop it. Yeah, these are fragile. Okay, here's your question. First question of the evening. Is it going to go faster, slower, or same speed through copper?
Slower.
So here's what it does. And note which way it was aimed. Oh, came out. All right, turn it the other way. Now, question, we turn the magnet over. Faster, slower, or the same speed?
Same, I think.
Same as before.
Now,
Faster.
I have to admit, I did not keep track of which side.
Oh, well, then now you got the wrong side because it's going the same rate. Turn it over. Now do it. Now watch. Was that a surprise or what? Okay, what's going on? What's going on as the magnet drops, and we listen to what Feynman says, there's an eddy current produced in the copper. That eddy current does something in turn. Solenoids, if you think of this as a one-turn solenoid, you can tell the direction of a field by turning your fingers in the direction of current, and the thumb will point in the direction of the field, North Pole up. But what it does is it will generate a current that's opposite to that. So it was going to go slow in both cases. There was no trickery on that, because what we did by turning the magnet over, the North Pole went the other way, the current went the opposite direction, opposition was still there. But the key thing that I want you to take away is electricity and magnetism are really closely related, and that's what this was all about. Electricity and magnetism, you don't have one without the other. Now, there'll be another demonstration later, but that's a common one with physics students that they do that. So let's move to the next slide. This part of my talk is, remember, it's a recipe. I'm going to give you a little bit of the chemistry. Niels Bohr started the idea of what an atom would look like, and he had noticed the spectrum of hydrogen, and there's a picture of what it looks like in a spectral tube. And he saw these lines at 410, 434, and so forth. And he suggested that maybe that is indicating that there's some quantum relationship to the electrons in the atom. So he produced a suggested idea of what that would look like. Bohr's model represents electrons with discrete energy levels. After an electron has absorbed a specific amount of energy, it moves to a higher energy level. It can fall back and emit a photon, which can be in the visible range. What I'm illustrating here is the 3-to-2 transition between orbits in Bohr's model. And the 3-to-2 transition emits a red line. Anybody that's looked at Dave Wexelman's pictures with a red hydrogen glow is aware that the universe has a lot of transitions that represent that red line. I was thinking of bringing a spectral tube here, but hydrogen is really hard to see the spectral lines in, so I didn't bring mine. I'm just going to show you the picture instead. This is the Balmer series. It's normally can be seen with a vapor tube and a diffraction grating, and that H alpha line is the one I illustrated there, the red one on the left side of the screen right over here. It's well known to all astronomers. the process that occurs in emitting the green line is a very similar process with nitrogen or with oxygen and nitrogen in our upper atmosphere that generate aurora colors. The green is an electron transition and monoatomic oxygen. What do I mean by monoatomic? It's not a molecule, it's not what you're breathing, it's basically an ion. When oxygen has broken apart and becomes an oxygen ion, there's an electron transition. And this is not a transition between orbitals like the hydrogen one I just illustrated. This is what is called a forbidden transition. Forbidden transitions are ones that don't obey the same rules that normal transitions. We can write in fact, Bohr wrote equations that fit those transitions. The forbidden ones don't fit his equations. So he wasn't necessarily able to calculate the electron transition in oxygen or nitrogen and so forth. The quantum mechanical model modified Bohr's fixed orbits to orbitals. We don't call them orbits anymore, we call them orbitals, which are probable locations for the electron. Like orbitals have specific shapes labeled SP, D, and F. I used to teach this a little bit in a chemistry class. Any of you that have taken chemistry in high school are familiar with those designations. And to help students remember it, I'd say Southern Pacific does fine. I don't know why I said that, but that's the way I always try to remember the orbitals in the atom. When atoms combine into molecules, the resulting molecular shapes are composites derived from these atomic orbitals. So I'm going to talk a little bit about atomic orbitals. First one is called 1s. It's in the first series, and it is spherical. And it's really a probability where is the electron in the atom. It's anywhere inside that sphere. It's like basically a basketball with fuzzy edges. And the inside it could be anywhere. The next one is 2s. 2s has a node in it, a single node. The electron, this is weird stuff. There's a lot of weird stuff with quantum mechanics. I don't need to tell you that if you've looked at anything like certain experiments that quantum mechanics have done. For example, a thing called the two-slit experiment. Look that up when you have a chance. But a node is a place where the electron cannot be. Now, how can the electron be in either outside the node or inside the node without crossing the node? Well, it's got wave properties, and that's basically the explanation that I understand. So the node has zero probability of finding an electron, but there are two places in the atom in the 2s orbital where the electron could be found. Actually, 3s then has two nodes and so forth. We won't go into all that. That's not necessary. The next orbital out is called the P. Remember SPDF. And P looks like an airplane propeller, if you like, with nodes in the center and around it. And by the way, I drew these. And my drawing, I was going to try to make the edges on that fuzzy. And it was a little bit tricky, so I didn't put fuzzy edges on it. But you could imagine that there's a little region at the edge where it could be that it's not a sharp break at the line. That's 2px. Perpendicular to it, there's another set of orbitals called 2py. And in the in and out plane is a third one called 2pz. So those are the places in the p orbital that an electron could appear. If we move to more complex atoms, we see more shapes. And I don't think for our purposes tonight it's necessary to do that. I'll be able to stick with everything about auroras without going into the D and F shapes and without going into, there's another whole set of stuff that chemists do. I'm just putting your foot in the water. Chemists deal with what happens when two atoms combine to form a molecule, then you get molecular orbitals, and so it gets complicated, but we'll leave it at this. So diamagnetic materials, all paired with paired electrons and weakly repelled by external magnetic fields. That's a definition. And I'll show you what a paired electron is here in a minute. Paramagnetic fields have unpaired electrons temporarily slightly attracted to magnetic fields. And finally, ferromagnetic materials, iron, cobalt, nickel, and there's a bunch of materials that are rare earths that are also ferromagnetic. There's really a third type. There's more types than that. There's a new type called altermagnetism, and that was just announced, by the way, in August of this year. And there are also ferrimagnet materials. And the difference between ferro and ferri is, well, I'll show you here in a minute. That's basically the orbital diagram for hydrogen. And if you think about the periodic table, those of you get a little bit with chemistry and periodic table, remember hydrogen in the upper left-hand corner. And that's filling a 1s1 orbital. On the right side, you're now over here. Oh, okay. On the right side of the periodic table, you're on to the 2s or 1s2, and I'll just show you that. All right, so I just mentioned hydrogen with the 1s orbital, and if we go to helium, which is over on the right, that's going to be your 1s2 orbital. And notice something, helium has a paired electrons. Now, what I'm dealing with here is here's the energy level going vertical on the axis here. This is the vertical axis. 1s now has a paired electron with helium. And so helium, you would conclude, is what? Somebody? Anybody? Are you asleep? It's diamagnetic because
I was so close.
you had one of three to guess and you guessed wrong, but diamagnetic materials are paired electrons. And so this really combines with what chemists are looking at. They say, gee, that orbital is filled and helium is unreactive, and that's one of the reasons. But hydrogen is very active. It doesn't have its orbital filled. Let's go to the next one. The next one in the periodic table would be lithium. It has an unpaired electron and in the 2s orbital, and therefore it's paramagnetic. Then we fill that orbital with helium. Helium. No, I'm sorry, I'm saying that wrong. 4 is,
Beryllium.
yeah, no, it's not beryllium, it's beryllium, you're right. 5 is boron, and boron again has a single unpaired electron. Some of this gets a little sneaky, so we don't want to get into, but boron is actually paramagnetic, even though you would, it's actually diamagnetic, even though you say, gee, it has an unpaired electron. And the reason it is because it forms a molecule. And the same thing happens with nitrogen, for example. So 6 is carbon, 7 is nitrogen, 8 is oxygen. There's the electron arrangement of oxygen. Next one after oxygen is, trying to think, fluorine. And the next one after that is neon. So neon, again, now has everybody filled up. It's unreactive, and basically that really says that it's also diamagnetic because they have paired electrons. So I wanted to just at least give you some definitions on electricity. That's as far as I plan to go on that, but I want to show you ferromagnetism. There's a specific kind of microscope called a Kerr microscope that can look at the crystals in iron. And this is an example of iron crystals. And the little dark lines right along and through here, you see, you see them also shading over on this one. And those are ferromagnetic areas where the iron atoms have lined up automatically together to whatever field it was exposed to when it cooled. Now, iron crystals are normally already have that property, but if it's exposed to a strong magnetic field, the magnetic field can move those domains. That's what's called a domain, and it can align the electron spin and the orbital motion. Let me just say one thing about electron spin. It's a misnomer. Electrons are not like tops spinning around. The spin number is simply a quantum number, and all you want to think about is that physicists sometimes assign names to things that don't have much meaning. And the word spin, to me, is a misnomer. It should probably be A or B or 1 or 2 or something that doesn't do that. There's a magnified view of the one that's circled, and the view we're seeing looks like we're looking in and out of the crystal. And so I believe that the dots here, the white dots, represents one end of the magnetic field. It's from the picture, it's not possible to really tell which it is. It's a limerick time. I got some limericks, so this will wake up people that are starting to fall asleep. A scientist renowned for his brain studied domains of a crystalline grain. It wriggles when stroked and it jumps when it's poked. His colleagues declared him insane. That's an original, so all my limericks are original. I don't know if you'll like it or not, but you're welcome to use it. But I'm going to publish a limerick book one of these days, I think. One of the other things that I mentioned in that, the fact that the domains have gotten aligned with literally trillions upon trillions of atoms. I hear things like, you know, there's a billion atoms there. Well, a billion atoms you wouldn't even see. It would be smaller than what you could see. These numbers are, quote, I mean, I know I'm in an astronomy group, but the numbers are astronomical. And magnetic domains above the crystal, above the Curie temperature, become unmagnetized. And only when a material that is a ferromagnetic material cools will the magnetic domains form. And so what we're looking at is something like a volcano, which I took this picture in Papua New Guinea. That's another thing you should put on your bucket list, go see a volcano while it's erupting. But this was an amazing night. We saw it. We were in a boat going by this volcano, which, by the way, not this particular night, has accounted for a number of people being killed in Papua New Guinea. So fortunately, our boat was able to sail by without incident. But what's happening is there are certain rocks. They're called basalts and gabbros, and those rocks have magnetite in them, which is a magnetic material and does exhibit domains. So when it comes out of the volcano, it's way above the Curie temperatures, the rock is. So it's very, very hot. As the lava cools, it takes on the state of the magnetic field that it was born in, which is basically, it's born on the Earth. And so the Earth's magnetic field is then embedded into that magnetic crystal, and it remembers it. And it'll remember it for thousands and thousands of years. So because of that property of ferromagnetic materials, I guess you call them I don't know, whatever the people are called that are geologists studying this stuff, can go back for years and years and put together the picture of what the magnetic field of Earth looked like at the time. I did want to show you one thing, and I put this thing together here. This is basically that magnetic fields are poles. They're bipolar. And for that reason, when you go away from a dual-poled object, you'll see that the field strength decreases as 1 over r cubed. Whereas if you look at a gravitational field, we say, well, it's the all of you know about the 1 over r square law. In effect, if you go away from the sun, how's the gravity? at the Earth? Well, it depends on the distance, 1 over the distance squared. But if you look at the magnetic field, it should drop by 1 over r cubed if you're outside the general area of where the poles are, if you're far enough away. If you're real close or inside that, the 1 over r cubed law breaks down. But it is a basic idea of magnetism that it is not a square distance law. The magnetic field refers to a region of space where magnetic force exists. The magnetic fields can be represented as vectors with magnitude and direction. They can also be visualized by imaginary flux lines, which are drawn from north to south. That's by convention. I don't dislike magnetic field lines, but I want to emphasize they are imaginary. Magnetic fields are continuous as far as we know. I don't believe they are quantum fields, but they could be. In any case, these are imaginary lines. But you'll see a lot of literature talk about the magnetic field line breaks and reconnects. I'm not sure that's 100% accurate. The field here is a basic dipole. And when the lines are close together, we say that that's the flux density is high. Flux density refers to lines per square area or per area. When the lines are further apart, the flux density is low. And flux density is measured in a unit called the Tesla. So I want to display a magnet probe. So if you turn the lights on again, and I'm going to pass something around here. I'm going to pass 2 things around, maybe 4 things. This is a magnet probe. And a magnet probe is just a little magnet on a 3-dimensional, it's on a, what do you call it, a gimbal, I guess. So it can point anywhere. So you can look at, in fact, this is something, these are built for students in 8th grade or 10th grade. They're not professional grade. I bought these for like $12, which is outrageously priced, but it's still cheap. And you can see that magnets do not have, just like a compass, it's not here or there, it's a 3-dimensional thing. And looking at a magnet probe, here's a magnet probe. You want to see, kind of investigate it, see how the magnet probe will point to different areas. Here's one that says Georgia on it. So this is a refrigerator magnet. These are safe magnets, not like my other one. And you can kind of investigate where's the North and the South Pole using a magnet probe waving around it. And it does show an important point, and that is that magnetic fields are not 2-dimensional, they're 3-dimensional. So keep in mind that that's really important when you look at the Earth's magnetic field. We're going to look at the fact that the Earth has poles, and the magnetic fields that are the magnetic field lines from the Earth are 3-dimensional. So we talk about that, before I do, I think of one of the things here, I forgot I was going to do this one. A coil with current also generates a dipolar field. The imaginary flux lines are no different than the permanent magnet that you just saw. So we can actually, just like Feynman's quote, we can generate that exact same pattern with a coil of current in a solenoid. Helical current in a solenoid is equivalent to the helical columnar current in the outer core of the Earth. So that's how the Earth's magnetic field is formed, and that's by helical currents. And we'll look at that on a later slide. Question. This is your first quiz question. We have been going through a bunch of heavy-duty stuff, so let's do a light-duty one. What do you think the magnetic field of the... Oh, I'm off camera. Okay, well, I don't know if anybody wants to look at me. I just want to say that what is the flux density in outer space? Somebody give me an answer.
Small. Same as it would be otherwise.
No, it's actually, I'll show you the answer since no one wants to volunteer and embarrass themselves. It's about 1 Tesla. Okay, okay. That's your first quiz question. That's the kind of quizzes I give. These are really easy questions. And so anyway, that was in honor of sending the Tesla out in space by you-know-who. Here's a way that students often visualize magnetic fields by tossing iron filings on it. These are some, I had these magnets, I was gonna bring them and I can't find them anymore. I don't know if when I had it out at school, whether they grew legs. Magnets can do that. And I don't know where they are, but anyway, that's a picture of 2 magnets together and just sprinkling iron filings. And I have to do true confessions here. I cheated a little bit with a picture because the holes were covered with filings and you couldn't read the N and the S, so I did a little Photoshop to clean that up, but it was not to deceive you because I just admitted to it. So you should understand that's a little bit of Photoshop work. And you'll never find anything like that on the internet, of course. The imaginary field lines are visualized with the aid of iron filings, which I just illustrated. All magnetic fields have their genesis in moving charges. So where's the moving charge? Permanent magnets have the ferromagnetic constituents and electron motion in the domains that we talked about, and that's the moving charge that creates a, quote, permanent magnet. So when I pass out these magnets with a magnet probe, those magnets are, in effect, being generated from, those magnetic fields are being generated by electron motion in the iron. Moving charge in metallic conductors is electrons, and this brings up something I'd like to kind of clarify, and that's the definition of current. A problem is that Ben Franklin said, okay, I see this current, and he saw electrons moving in a wire, or at least that was he didn't know that. He didn't know which way they were going. He didn't know electron from a proton because at that time they hadn't discovered it. So he defined current as a direction from plus to minus. The problem is that in metallic conductors, it's the other way around. The definition has not changed, but electronic people, and I was one for a while, object to talking about current as plus to minus. I don't personally object to it because that's only part of what I do. I really want to see what's the science. The true science is that the definition is from plus to minus, and there are charges that move from plus to minus. For example, plasmas, or if you look at charges inside a battery, you're seeing ions move, they're positive ions. So the word, the direction of current, you have to be careful when you see definitions anymore as to what current are you talking about. Are you talking about current as defined, or are you talking about electron flow? And the answer should be, I'm talking about current as defined. So that's all I use. I don't talk about electron flow. Okay, then we also have, how about the Earth's magnetic field? And that's mapped with a particular thing called the World Magnetic Field Model. And World Magnetic Field Model shows the intensity. These are not vectors. They're not showing the inclination. Remember that it's a 3-dimensional object. They're just showing the magnitude of the field as you look at the Earth. And there's some interesting little points on this map that I want to show you. There's an area right here called the South Atlantic Anomaly. In the South Atlantic Anomaly, the magnetic field drops to like 23,000 nanoteslas. Nanotesla is the common unit people use. They could say the microtesla. If you like micro better, you'd say it was 33 microteslas or 23,000 nanoteslas. Now, the global average is much higher. And in fact, because of this very low magnetic field strength in the South Atlantic, satellites have to be deprogrammed or watch out for, or in any case, they have to take precautions with satellites that traverse that area because the magnetic field is weak and the radiation from the sun, the solar wind, can seep in there easier and damage sensitive electronics. Now, there are two places. By the way, all the dark lines are 5,000 apart on this map. So the first one outside the 23,000, right over here. Are you seeing that? Yeah, you are. That one is 25,000. And the next one's 30, 35, 40. Notice the United States is somewhere between the 45, 50,000 nanoteslas. We keep on going and we get up where the pole is, the magnetic pole, and the strength is up to about 60,000. Notice that the South Pole, 60,000, is still not near as close to the pole. It's 65,000 is closer. And a second thing about the South Pole is the North Pole is within a few degrees of the true north, but the South Pole is not. So there's some stuff going on down there in the generation of the field. The North Pole is actually inside the Arctic Circle by quite a bit, and the South Pole is outside the Arctic Circle. All is quiet on the Western Front. Okay, evidence from volcanic rocks shows that the South Atlantic anomaly is a recurring phenomena in the Earth's history, that it's been around for at least 11 million years. So if you read some of this stuff that you'll see online, you'll see some things like the world is coming to an end, the magnetic field poles are going to reverse, and so forth. And it's all scare tactics. Don't lose any sleep over the reversal of the poles. That's my advice. I don't lose any sleep over it. I wouldn't do it. Magnetic field is a vector field. Remember, we say that it's got two things that create a vector, magnitude and direction. So it has to have a magnitude, how strong is it, and which way is it pointing. That's what a vector is. So the intensity map on the previous slide only indicates the magnitude of the field, and this one actually only shows really the surface direction. Look what the field's inclination is at the equator. The line that's drawn in the middle there is just the horizontal line. Where is the magnetic field horizontal? It's not actually right smack on the equator. It's off from it a little bit. And you also will notice that there is a line here at the north magnetic pole and the south magnetic pole, which points straight down to the center of the Earth. And that almost defines for us where the pole is. This is a little bit about the magnetic field as it appears when we involve the sun in the field that the sun is generating. The sun has an interplanetary magnetic field lines, and they are not necessarily in one direction or another. In fact, auroras depend a little bit on what direction the interplanetary magnetic field is when it strikes the Earth. South-aiming interplanetary magnetic field lines actually generate better auroras than north-facing ones. And I'll show you a little bit about what those look like when we move on here. There's a couple points to make on this slide I want to just point out. The magnetic field lines, which is basically, think of it as string, have a couple spots here where they go down toward the Earth. And those are places or nodes where charge can enter the Earth's ionosphere, which is where we are. There is no specific layer called the ionosphere. It basically happens that the ionosphere is just the area where there are charged particles, and it's part of the layer known as the troposphere. So I think what the shape is kind of interesting. It generates this magnetopause area, which is drawn out on the solar side of the Earth. It's compressed. On the night side, it's drawn out. And of course, the Earth is turning, and this thing is always pointed toward the sun. And the angle of the lines that are over here depends on how the magnetic field from the sun hits the Earth, and we'll take a look at that in a minute. Okay, magnetic field lines have two channels that are pointed there, left for charge to flow. We have some really great museums in Georgia, and one of them is up at Cartersville. It's a Smithsonian museum. And they did this scale model that you can look at of a cutaway of the interior of the Earth as best we know it. So at the bottom of the thing is the inner core. And the inner core I wanted to talk a little bit about. It's roughly the size of Pluto, about 1% of the Earth's volume. It's primarily composed of iron nickel alloy, but it contains lighter elements. And importantly, it contains about 3.8% carbon. You go, how the heck do they know that? You know, nobody's ever sampled it. There's a really interesting story about how that's done. I do have a lot of references to my talk, and I hope if you're interested in finding that out, there's a 2025 paper from Oxford that discusses how they figured out the 3.8%. They believe it's done, or that it is done because of what's called supercooling. For the Earth for the inner core to cool to the point that it's a solid, it has to, when you cool ice, for example, you basically have to first make the ice below, the ice water has to go below 0 centigrade in order to start the crystallization process, or you need a center of nucleation, it's called. Well, the Earth, like that, in creating a solid inner core, needs to have a center of nucleation for the liquid outer core to solidify to the inner core. And the only way they could come up with a calculation that shows that the amount of cooling was put in 3.8% carbon in their calculations. Other materials, every other thing they tried would not cool it properly. Again, I'm sort of brushing over the thing a little bit lightly, but I would refer you, these papers are online. You can go read them for yourself. If you'd like more information on it, please look at my references. I have a number of pages of reference that I'm giving you that you can find out more information, but I'm not going to spend more time on that. Okay, going on, that's the lower mantle. I don't think for our purposes, it's necessary to describe these other areas, but the mantle goes to the crust, and the crust connects to the neck bone and so forth. Here's the inside of the Earth, again, from another person's view. I borrowed this. This is USC drawing. The inner core is moving, and it should move approximately the same as the mantle. In fact, it doesn't. It changes its speed very slightly, a little bit faster, a little bit slower, and the cycle is about 70 years. And they can trace this back from, I guess, from earthquake data. I'm not sure where that data comes from, but we know it speeds up, it slows down. I have read recently 2 news stories online from places that look reputable that say the magnetic or the inner core has stopped in its reverse direction. You probably saw it if you look at some of this kind of news. That's not true. The Earth's inner core slowed down and reversed its direction in the sense of just slowing down. That's not really a reversal of direction. It's just a slowing down. So it's actually going, it'll actually go slower than the mantle speed. It'll speed up and go faster than the mantle speed. But it's an interesting thing. There's a cycle involved in it because it's suspended inside a liquid outer core. Now, just to show you what's going on with the temperatures in the inner and outer core are far above the Curie temperature. So the core cannot retain magnetism, either the inner or the outer core, because of their temperature. The Earth's magnetic field is primarily generated by moving charge in multiple complex vortexes in the outer core. This is a graph of the temperatures and the pressure in the core. The red line is the temperature, and notice what happens at this is the core mantle boundary right up here. And at the core mantle boundary, the temperature zooms up. It does that through, this is the crust down here. It gets much, much hotter. And one reason you can't get into the mantle, it gets kind of tacky and sticky, and the drills just can't drill into mantle territory easily. So the temperature zooms up to the mantle. It's still, the melting point is still above it for the rock. By the way, notice the temperatures here. This is over 6,000 degrees Fahrenheit or Kelvin, which is hotter than the surface of the sun. So the temperatures in the core are as hot or hotter than the surface of the sun. And the pressures are super high. And if you've taken, again, we go back to chemistry, if you look at the state of equation, the equation of state for materials, that determines whether or not a material is a solid or a liquid, depending on its specific melting point. And so as the melting point crosses that boundary, that's where we basically convert the outer core is freezing and becoming the inner core at that point. I hope that's as clear as mud. This is basically the solid inner core surrounded by a liquid outer core. And the liquid outer core is primarily a plasma. Basically, it's ionized. It's so hot, electrons don't stay with their atom, and the atoms are ionized, i.e. there's charge. And whenever there's charge that's moving, that's a current, and the current itself is moved by convection. And it's also circulating. So a circulating charge generates a magnetic field. So the magnetic field of the Earth is generated by a liquid outer core with circulating currents. I've seen different references that show what those currents look like. And I chose this slide, I basically adopted from Lowry's book. And Lowry's book I brought with me, if anybody's interested. It's this one right here. And basically, Lowry's book has that picture. Again, I just sort of converted it as to how the core moves. And if you're curious, there's an area here above the solid core, which is in the direction of north, which is basically the rotational axis of the Earth. And that rotational axis creates, there's a shadow region here. And that shadow region does not have as much current. So most of the magnetic field of the Earth is generated outside the shadow region of the solid core. It's generated in the liquid core outside the shadow region, but there's some that's generated in both. Lowry has a nice discussion of this, and I highly recommend his book if you want more information on that. In addition to the Earth's dynamo, there are other contributors to the magnetic field of the Earth. The magnetized ore bodies, as well as certain rocks I mentioned earlier, basalts and gabbros, which are magnetite lavas. Gabbros basically are lavas that's cooled slower, and basalts are cooled faster, but they're both composed of the same material, and so they do contain ferromagnetic materials. Electric currents in the ionosphere, the magnetosphere, and the oceans also have transient currents in them that generate magnetic fields. Most of the time you're going to hear of a thing called the virtual magnetic field of the Earth. And when they say virtual magnetic field, they're saying that we want to just use the calculation based on a dipole, so we don't deal with these other processes. We use a simple dipole model, and then what we call a virtual field. So here's a simple dipole model on the left, and on the right, a super detailed computer simulation of what the Earth's magnetic field actually looks like. The colors on the right represent whether the magnetic field is north-facing or going north or going south. And I thought, well, you know what would be interesting? These were two different authors. That was NASA on the right and Wikipedia on the right and NASA on the left. And if you do this and overlay, interestingly enough, the dipole field looks pretty much like what the calculation is if you get away from the area of the Earth itself. I thought that was interesting. That was an idea I had to just show that. This is another thing that's going on, and this is one of the alarmists have been screaming about, and again, I pretty much ignore it, but if you like to be alarmed and jump up and down, set your hair on fire, the magnetic North Pole is moving towards Siberia, and it's moving very rapidly. And the field is about 9% weaker than the historical average. And I said, despite this, the North Pole is still less than 5 degrees from the true north, and the intensity is within 10% of the historical average. But the pole started racing away from us, and so Russia's getting, it's on the path to go to Russia. I don't know why it wants to go there, but that's what it's doing. And that's one of the things that the geologists, a lot smarter than me, are trying to figure out why. This is another paper that I read that I think is really kind of ties a little bit of this in the ribbon. This is basically this VGADM. VGADM is it's basically the virtual geomagnetic axial dipole moment. And by the way, that's a mouthful. I want everybody to say after me. Virtual geomagnetic axial dipole moment, and not slur your words. But anyway, when you read this graph, the red line basically represents the magnetic field strength, the flux, and the blue line represents the oxygen. And what's happening, we read this back in time. Most of the time when you do a graph, everybody knows this, you make increasing time go to the right. Well, this graph, when you're doing historical stuff, you sometimes go back in time. So notice that 0 is on the left, and further back in time goes to the right. So if you want to think about time advancing, think about moving from right to left. And you'll notice that the magnetic field and the oxygen seem to track each other. And they've done that fairly close, although you see all these, the dipole moment seems to have more shakiness than the oxygen, but they do correlate. In fact, what they've done, a recent study, which I referenced where I got it, this is just this year, this publication came out, and I wrote to the authors of the paper and said, what do you attribute the fact that oxygen and magnetic field strength of the Earth are correlated? Why? And they wrote back a very nice email to me, and this is part of the correlation coefficient right here. It shows, and again, the oxygen in blue and the magnetic field strength over hundreds of millions of years, up to 500 million years, have correlated. Now, I thought that was really interesting, but why? And the authors of the paper don't even agree as to why. And the one author wrote a nice letter back to me, or an email, and basically said his view was, and he gave me his view, basically it has to do with continental drift and so forth. And I put that in, if you look at comments, you can read the email yourself and see what he has to say about why these two are correlated.
Dave?
Yes.
Where is this oxygen measured? Is this oxygen in the core, oxygen?
No, that's atmospheric oxygen.
Atmospheric.
Yeah, what you're breathing right now.
Interesting.
Atmospheric oxygen is closely linked to the magnetic field strength of the Earth. That's a little weird, isn't it?
Yes.
And the correlation is quite good. That means that we know that the two are related. What's the relation and why is a question. And that paper was just this year. So again, I don't have the answer to it. I'm just presenting the question, and you can enjoy finding the answer yourself or whatever, or read the paper, I would suggest. The Earth's magnetic field and the correlation to oxygen. Oh, I'm sorry, that title is not correct. It should have been, I'm going on with the atmosphere deflecting charged particles around the planet. In 2008, the effect of the solar wind on the Earth and Mars lost 10 times more oxygen by percentage than the Earth due to this gust in 2008. And I think, wow, so the magnetic field is helping us keep our oxygen in some way. And so you might say that if we lose our magnetic field, what happens to our oxygen? And you know, if we don't have oxygen, what happens? It's not good. Okay, I'm going to have in a minute a model that I'm going to pass around of the Van Allen belts. There are two toroidal-shaped radiation belts, and we've done this model. It's an important model that I'm giving everybody a copy of the model. And so you'll get a copy that you can keep or do what as you like. And I'm going to ask Todd to help pass it around. Rachel wants to, that's fine. There's models for everybody to get one of the Van Allen belt. Now this is the outer Van Allen belt. So could we have some room lights while they're passing that around? And I probably should have one also. This is what the model looks like. Can you see it? It's suspiciously like a donut, but it's not a donut. This is a model of Van Allen belts. This is the outer belt. Now do not bite into the model at this point, because I have something for you to do. Can I go to the, stay on camera or do I?
Thank you very much. Thank you.
Okay.
Yeah, wait for your morning coffee.
I was starting to see eyes glazing over, so I decided to unglaze your eye a little bit. All right, so is this okay? All right, I want you to take your finger, stick it up in the air.
You don't all have donuts.
Twirl it. You don't have a donut?
No, we don't have donuts.
They're still making it around. They're coming. All right. We twirl our finger, stick it on the bottom of the donut, out in the dough area, spinning it around. Now move it around, pointing to the donut, and move it around the top. Keep spinning. Now come back around, keep spinning, go back down. Now, are you an electron or a proton? I don't know. It doesn't matter. They spin in opposite directions, but most of the Van Allen belt, the outer one, is electrons. So you should take your spin and go a little bit to the west each time, because electrons will drift to the west. One more thing before we call it a donut and eat it, and that is there's another current that circulates this donut, and that's called the circulating current. No, there's a current around the donut, and that's called the ring current. I was having a serious senior moment, which I have a lot of these anymore. The problem with senior moments is when they start running together, and that's starting to happen. So if you want to shape your donut a little more, you're welcome to do that. And what I'm going to do is I'm almost done with part one. I want to finish part one, and then we'll go into part two, which is auroras. And part two will not be very heavy-duty science at all. So that should make people happier, I hope. Those that are getting more. But the total mass of the Van Allen belt, the total mass of the Van Allen belt and this donut are probably close to each other. The total mass in the Van Allen belt is 11 grams. Unbelievable. And the particles in there have a velocity. Remember, you were running your particle. This is basically called a magnetic bottle. And the magnetic bottle of the Van Allen belts, that electron in the Van Allen belt moves from top to bottom in about a second, depending on its energy. About 1 second from the North Pole to the South Pole and the South Pole back. So it's very, very fast, relativistic type speeds. And basically, okay, let's move to the next. Separate population of charged particles. I don't want to eat it now. I will save me one later.
Thank you.
A separate population of charged particles, primarily protons, overlaps the outer belt and forms an electrical current called the ring current. And the ring current moves perpendicular to the magnetic field lines. And remember, there's no force when it's moving perpendicular to the magnetic field lines. The protons have a longer lifetime in the ring current and therefore dominate over electrons. Now this is basically a magnetic bottle, And I called this slide Van Allen Belt's Nature's Tokamak Question. Tokamaks are devices that are trying to retain fusion energy. And the magnetic bottle of a tokamak basically does what the Van Allen belts do, and that is spin the electron when it gets to the end of and those coils are generating a magnetic field. And the magnetic field lines, if you draw lines for it, are not straight parallel lines, but in conservation of the energy of it, it goes faster and faster as it gets closer to the coil. And it gets to a point where it just reverses and goes back the other way, tighter circles. So that's basically called the mirror point. And the Van Allen belts, you already saw, they run around your donut from the inside to the outside and in these tight circles. So here's a more realistic picture of what your donut would look like with a charge of electrons moving around in that shape. That's one of the Van Allen belts. There's a mirror point where it reverses, goes to the other side, and it takes about 1 second to make that trip. And electrons, that whole coil is drifting in one direction. The most energetic electrons have deeper mirror points than electrons, hence most auroras are driven by electrons. Proton auroras, while much rarer, can occur. Proton auroras linked to the plasma activities within the ring current. And we'll look at that. This is a picture, and you can see here, the dotted area here is the plasmasphere, which is basically the outer Van Allen belt. And the ring current is the blue line going around here. And there's another ring current out by the plasma, at the plasmasphere. I think I backed up accidentally. And that the strength of the ring current is measured by a property called the DST, which is disturbance storm time, and it's measured in nanoteslas. Some of the aurora chasers prefer to watch what's happening to the DST to determine how strong the magnetic field is, because the magnetic field, when it's very strong, drops the DST and it goes down. So on a strong magnetic field, or a strong storm, it'll drop by 30 nanoteslas. This is a thing called the Birkeland currents. Birkeland was around about 1905. He did this experiment. He won a Nobel Prize in his understanding of Birkeland currents, but these are basically currents with a magnetized sphere. And the sphere was in a chamber. It's right there. And this is a picture he took back in the early days of photography. And those are called Birkeland currents, which are also known as field-aligned currents. They're variable currents that flow along magnetic field lines and connect the magnetosphere to the ionosphere. Birkeland currents tend to be pinched into filament structures due to self-generated magnetic fields. And here's a picture. It's pretty common. It's online. I don't know who drew this, but I picked it off of Wikipedia. There's a couple of Birkeland currents, and one's on the day side, one's on the night side, and they go in, the two regions go in opposite directions. Remember, electrons are going the opposite direction of current. So if you talk about which direction is the current, it's the opposite of the direction of the electrons. Now there's also a thing called the Pedersen currents. That's what amateur radio operators depend on when the ionosphere is closing in at night. It does it every night. The Earth, remember, is turning under this. The part of this is basically from the sun, and it stays more or less in position, but the Earth is turning under it. So think of the Earth turning under these currents. And that's why the ionosphere changes over the course of time as the Earth rotates under that current. That's called a current sheet. The rotation of the Earth accounts for part of the changing of the Birkeland currents. And also, this is showing just the north, and there's a complementary Birkeland current in the south. Okay, associated with Birkeland currents are waves called Alphen waves. Alphen waves. Alphen waves are plasma waves caused by wave-like variations in the magnetic field itself. They carry energy through empty space. They're characterized by low-frequency oscillations, and they are very important to astronomers. So an Alphen wave was, we have a limerick first about that. So here comes another limerick if you're ready for it. Okay, this is Alphen himself. A Yale student from Upper New Haven asked a question that he had been saving. How do Alphen waves go? I hear they move slow. Are the magnetic field vectors waving? And the answer to his question is yes. It's the magnetic field vectors that are waving. And the important point about that is they are in all plasmas. So astronomy, they're fundamental energy transfer mechanism for plasmas, and they play a role in heating the suns of corona. There are many astronomers that believe the very high temperature in the corona is due to these Alphen waves. And here's a NASA simulation of what they might look like. You can see electrons acquiring energy from the magnetic field as the magnetic field waves. And so this is what his proposal was. He won a Nobel Prize for this in 1970, I believe it was. And in fact, he's no longer with us, but he gave a talk at Alaska where they do Aurora studies on Alphen waves. So this is important in many areas of astronomy. It includes anything that has plasma and energy transfer. And as you know, 99.9% of the universe is plasma. So Alphen waves are pretty important.
Are they density waves?
What'd you say?
Are those density waves that we're seeing there? Where you put one pushes on the next, pushes on the next? Never mind.
Density waves.
Density waves. Oh, I'm sorry, I couldn't hear. The question was, what are they density waves? As far as I know, it's the field vectors themselves that are doing the waving. Whether that implies a different density in the magnetic field, I'm not sure. So I'm sorry, I can't answer the question. I can't honestly say I know. So, but they are magnetic field vectors that are waving, and they're imparting energy to electrons. So they're very important. And there's a really good paper, which I referenced at the back, on these waves. And if you'd like to read the paper, it goes in quite a bit of detail. It's not heavily mathematics, although if you want to get into heavy mathematics, you can. So the next thing is on the magnetic field pole reversals. There's a weakening going on of the SAA, as I mentioned, the South Atlantic anomaly. Some scientists think there's a reversal on the way. And I say, as far as the reversal is concerned, I'll use the Yogi-Berra solution. It's tough to make predictions, especially about the future. So if you're interested in more gory details about what's going to happen to us if we have a magnetic field reversal, this is the book I would recommend. There's things, I put a bit of my review, you can accept or deny, whatever. My review of this book is, it's a pretty interesting book, but it has no pictures, it has no graphs, it's just words, and it is written on a layman's level. So if you're interested in finding out what Alana Mitchell says about magnetic field reversals, this would be a good book to find it in. But she's a little bit of an alarmist, and I happen to not be an alarmist. I mean, when you're 86 years old, it's hard to be an alarmist. That's my view. But in part of the reversals was an actual reversal that happened about 41,000 years ago. It didn't last for a huge amount of time geologically, but human-wise, it would have been a long time. It was a few hundred years. And there's plots of what happened when the magnetic field dropped to less than 10% of its current intensity and displayed a highly non-dipolar configuration. So it didn't look like a dipolar magnet at all. There are auroras seen in the Netherlands by the Neanderthals, and early humanoids. The center of the aurora oval is indicated by a red circle, and I will pass on that part. Let's move on. There's the red circle, and there's the path it had taken. That's not the, I don't believe that's the North Pole. The pole did a totally different thing than that. This was the center of the aurora oval, so it's sort of perpendicular to the pole. And here's the pole motion itself, based on the American Geophysical Union. And how do they know this? Basically from those ocean cores that I mentioned earlier. The extreme radiation and excursion has been blamed for the extinction of the Neanderthals. In any case, they probably suffered from sunburn, as did early humanoids. And to illustrate, I did this. And John said he could take a joke, so I put him there. This is part 2, the aurora. So we've reached the point in the talk where take a break. Part 2 is going to be less scientific and more pictorial. But I thought I'd throw in one more limerick that I composed specifically for this talk. So enjoy. Here it is. An electron at very great height escaped from his prison one very dark night. I'm in this thin air, I don't have a care, and he burped a green photon of light. Hope you like my limericks. I may publish a limerick book one of these days. I don't know. This is I'm going to cover a little of the basics of auroras and how they're formed and so forth. That's a picture, by the way, that I took in Iceland one very great night. It was 2013, October 2nd, 2013, a night we'll never forget. And I have a story about this aurora that's in the comments. I'm not going to repeat it here because of time constraint, but if you'd like to read the comments, and the comments are on your drive, about the story of this particular aurora, you might find it kind of fun. One of the issues with the sun's role in auroras is the sun generates, as everyone here knows, the solar wind. Solar wind is a stream of charged particles emanating from the sun. Electrons and protons are the primary constituents, although there are some other ions as well. A proton is nothing but a hydrogen nucleus without any other accoutrements like neutrons, although some hydrogen has the neutrons sticking around. That's called deuterium. That's a different story. But one of the things that people looked at early on was the fact that comets have a tail pointed directly away from the sun. Comet Hale-Bopp and some others have a comet that points away from the sun, the blue one, and another one that's called the dust tail. The blue one is an ion tail, and the ions always point away from the sun because they are driven in that direction by the solar wind and go very fast. The dust tail basically says, here's where I've been, and I deposit a little dust as I went. So the trail of the comet and where the sun is are sometimes two different things. That's why you can have a two-tailed comet. The sun creates a variable and highly complex solar wind. And when the solar wind is highest, aurora activity goes. And so the sun is so hot, the temperature is so high that the corona can accelerate material so that past the escape velocity of the sun, which is 617 kilometers per second to escape the sun. By comparison, if you're interested, is the escape velocity for the Earth that astronauts had to do to get to the moon was 11.2 kilometers per second. So that's the difference in escape velocities. During a solar maximum, solar wind becomes faster and more turbulent, and the heightened activity results in increased solar flares and corona mass ejections. At solar maximum, the sun's magnetic field reverses polarity. And by the way, this shows basically where we are right now. It was an Irish soldier, Edward Sabin, that back in the 1800s published a paper showing the connection between the solar activity and aurora activity. He saw that there was a connection, there is, and I would just encourage everybody, if you possibly can do it this year, it's a great year for the solar, and the best time of year to do it is spring or fall. And the reason for that has to do with the position of the Earth's pole with respect to the fact that of the season. There is a seasonal variation. The best season is spring and fall. March is a great year. You can't sit too late and the light will get you, and too early and the cold will get you. So you want to try to position your trip in March is the recommended date. You can still see them in other times. And Dave may correct me as, did you notice a difference in seasons when you lived in Alaska?
I tried to, but with the it was mainly when it was clear you could see the aurora.
Yeah, we saw, I was at, when we were at Chena Hot Springs and we stayed there for about 10 days, we saw it every single night we were there.
Yeah.
Now, some nights it doesn't show up until midnight, but it was there every night and it was clear every night. We had a wonderful experience there. Because of the time constraint that I'm doing, there was a coronal mass ejection video here. It's pretty good. I'll do it, it's short, but we're gonna look at this. Here's a coronal mass ejection. This video was produced by NASA, and I thought it's pretty good. It shows not only the material coming off the sun, but you'll also see how it interacts with the Earth's magnetic field. Here it comes, and it causes the magnetic field lines to in effect reverse from this to the night side. And as it reverses, the direction of the fields on the directions of these fields is opposite to each other. So when they connect, basically a huge burst of energy can then feed the Van Allen belts essentially, or find a path to the for charged particles in the ionosphere, which basically start the aurora going. So that was basically a NASA simulation, which I thought was very good. So the solar wind carries its own magnetic field together with a solar dynamo and other sources from the interplanetary magnetic field. And the interaction of that magnetic field with the bow shock, about 10 to 15 Earth radii upstairs, is called the magnetosheath, and it extends the teardrop tail approximately 100 Earth radii magnepause away from the Earth on the night side. They're analogous in effect to if you had a rock in a river and you watch what happens when the water hits the rock. There'll be a bow shock in the front and a tail in the back. And you could think of the magnetosphere as something on that order. So that's the way I would look at it. The solar wind is composed, as you know, of electrons, protons, ions. And the fast solar wind, there are two solar wind components. There's a 550 kilometer or better component, and there's one that's less than 450 called the slow solar wind. And they come from different parts of the sun. They're both supersonic, though. This is one thing I mentioned, that the aurora oval is not a nice smooth oval. And it is turning because basically the oval is produced by the Birkeland currents from the sun. And remember, the Earth is turning under this oval. And the Birkeland currents are concentrated, so there are bulges wherever that gets larger. So there's an interaction of the Birkeland currents and the aurora oval. Around midnight is typically when it's most active, although it can happen all evening, anytime. In fact, the best one I'd seen in Iceland actually occurred right at dinner time for us. So that's part of the story, by the way. We were in a very large room with a lot of people, And somebody said there's an aurora outside, and you never saw a bigger crowd running for the doors. And it was almost a stampede, and there was desserts left uneaten that night from dinner. You can read more about it on that talk. The polar satellite, which is one of NASA's satellites, has viewed the fact that there is a similar aurora on both poles at the same time. That's called auroral conjugacy. And basically there's also Birkeland currents at both poles, as I mentioned. So there's a mirror effect on the two poles. So there's a southern lights which correspond almost identically to the northern lights. That was suspected for a long time, but it's now been proven. From space, the aurora forms an oval around each magnetic pole. In this view, south pole, this is the south view, that's our Antarctica right there in the middle. And the typical aurora oval is not a nice symmetrical picture, but it depends on where those currents are, as I mentioned. This is a theta aurora, which basically has, it looks like the Greek letter theta, and there's a line that connects, oops, I didn't mean to hit that, but there was a line across the oval that connects both sides. That's called a theta aurora. I mentioned that there's different ways that we know, well, we want to know, gee, should I go out now or what time should I go? Well, there's a prediction center. And again, I have a reference in the references to where to go to the prediction center. But the prediction center will show you whether it's unlikely, which is 0, up to extremely, well, not only likely, it's going to happen, and you just have to be aware. An aurora of 9 is very, very intense. That's the highest score. There's another one called the G scale, and I'm not going to talk about the G scale other than to say it more has to do with damage than it does with what the aurora looks like. I think the best scale to look at is the KP scale. I don't know what KP was standing for, but I should have looked that up, but I don't have that number. But you can go to the Space Weather Prediction Center and get a typical KP. This is one I just went over there one day this last summer and said, I wonder what the aurora is going to look like tonight. And here's what you get on that site. And that's a NOAA site. And so if you're curious, is this a good time to go look at the aurora? That'll tell you. I wanted to summarize a few places that you could go. I think if I had to list them, I only listed 3 of them here. I would have to say Chena Hot Springs is my #1 choice. It's in Alaska. It's about, I think it's about 60, if I'm not mistaken, about 60 miles from Fairbanks. They have a lot of stuff in the daytime. You can do dog sledding. You got hot springs, which is wonderful. You can do snowmobiling, sleigh rides, et cetera, et cetera. Iceland, there's a lot of sightseeing. There's geysers, there's hot springs again, and so forth. The best time of the year and which one to go to also depends on weather. And the typical weather is better at Chena Hot Springs than any other location I've seen, and the cost is lower. So that's why I put it down to #1. Iceland is great. It's got some wonderful stuff to see. I'd highly recommend a trip to Iceland if you can, but it is a little pricier, and it does have a better chance of not having good weather. That's me in Iceland. I don't know who took that picture. I guess Lorraine did. But I don't know what I got on my face there, but I guess it was sand or something from the bottom. But this is the Blue Lagoon, the famous Blue Lagoon, which has been threatened by lava flows recently. And these are a few pictures of what I liked about Iceland, some of the scenery and waterfalls and so forth. So I put a couple of my favorite spots in Iceland on that slide. There's a book that will describe places to go that had a brief mention of Chena Hot Springs. It has some other ones. Now, I've never gone to northern Canada. There are specific places in northern Canada that cater to tourists and have some wonderful things to see, it looks like, from the literature. But this book, it's not a very expensive book, but it describes all these different places because This is a serious Aurora chaser that wrote this book. I consider myself a interested party, but I've only been to these locations mentioned. I've seen it in North Dakota, Alaska, in 2 places, and in Iceland and Norway and Svalbard. Here was an aurora that happened March 30th, 2001. And what happened was the KP went up at one point to 9, which is a storm. It's like an every few years type of storm, fairly rare. And here's this picture that I took on that evening, standing outside my house with my neighbors who are here in Cedar Ridge. And I took this picture from my house on that evening. I was unaware, I hadn't been looking to see what the KP was, but what happened was I had my grandson out with me in my observatory, and I had left the roof on, and I said, oh, I'm gonna go out and close the roof, and I walked outside, and oh my God, there's an aurora going on. I couldn't believe it. So I ran back in, got my granddaughter who's here tonight, and she doesn't remember it, I don't think, because she was kind of young, and my grandson. We went outside, and then I called the neighbors, and other people got mad at me later because I didn't call them, but I wanted to go see it. It was moving a little bit, but it was wonderful. And Jim and Kathy can tell you their impressions if you ask them after the talk here. Solar storm of March 30th that we saw in Cedar Ridge was seen elsewhere in the country, and I took some pictures from Boise. Here's one from Sacramento and one from San Diego. Found these on the internet, by the way. So I put the credit there for who took those pictures. This is the KP for the solar storm just last year. May 10th, there was one. I tried to see it in Georgia because I knew about this high KP that was going to happen, an amazing storm. And I stood out on my deck in Georgia and didn't see anything. All we got is crud up there. Georgia is not my recommended place to go see auroras. It's pretty far down the list. It's in about, I don't know, 10 to the 30th place. Okay, the solar storm of 2024 produced some beautiful auroras. This one was in New York. At least that's what it says here on this slide. I snagged some of these off the internet. Here's an aurora from Key Largo. This was again on October 2nd in Iceland. The KP in Iceland was only 6 compared to what the Grass Valley one was 9, but it still was an absolutely gorgeous aurora. It lasted and lasted and lasted. I was still out there a couple hours later, and it was going on. It was just a great aurora. So I'll tell you a little bit about the colors of aurora here in a little bit. Again, Iceland, same night. And by the way, the color in the bottom of the picture there was the sunset. This is very shortly after the sun hit. And of course, this time of year in Iceland, in October, the sun goes down kind of slow because of the angle that it's going down in. That night on October 2nd, same night in New York, this was the picture. And I'll explain the reason for the color in a minute. The reason why New York saw a different color. But it has to do with the atmosphere. First of all, our atmosphere is kind of strange in a way, but the higher you go, the thinner it is. Everybody knows that. But it also changes the ionization. The higher you go, the more ionization there is. And what happens is certain parts of the atmosphere tend to have oxygen ions. We don't want oxygen molecules. We don't like them. We don't want them. We want oxygen ions. I'll show you why here in a second. Let me kind of add a couple. There was an airplane going down at the bottom there. That's stratosphere, which is or troposphere, which is the lowest part of the atmosphere. And that's where you find all flights and stuff like that. The next level up is where the ozone is in the stratosphere. Next layer up is the mesosphere. It's the coldest part of the atmosphere. Auroras occur here occasionally. Then as we go up, the temperature suddenly starts to rise, and you might ask why. And I don't know for sure, but I believe the Alvin waves that we talked about, magnetic heating, I think has something to do with it. I'm not sure I want to be quoted on that, but if it's on YouTube, I suppose I will be quoted, but I believe it's the Alvin waves. One of the reasons that we don't like molecular oxygen is molecular oxygen tends to quench the oxygen, atomic oxygen spectrum. And I'm going to talk a little bit about that spectrum. Remember what we were doing early on the talk was showing you what the orbital diagrams are. And this is oxygen, atomic oxygen. Well, there's actually a couple of states within it. These are called forbidden states. They're not part of the normal movement of electrons from one SPD or F orbital to another, but these are the forbidden states in oxygen. There's a couple of forbidden states. I think there's 3 total that have, well, at least 2 of the lines that I've got written there, 557.5 and 630, which is a red line. And the speed, the transition of when the photon will be emitted after it was energized. How did it get energized? Ions or solar wind energized it. And it will emit a photon, but the transitions don't occur instantly. They're fairly slow. By emission standards, one of them is 3/4 of a second on the average time before it emits the photon. The red one's 110 seconds. Well, think about that. If oxygen O2 quenches it, who's going to get quenched the easiest?
The red.
Yes, the red, correct. And the reason that it's the red is because it has to sit around and not get hit by something else before it can emit a red. So where would you expect to see a red line in a red aurora? You'd expect it to be above a green line. And this is the reason right there. It has to do with the average quench time for the red and green forbidden transitions. Now, above 120 miles, the red from atomic oxygen predominates. But below 120 miles, green from atomic oxygen predominates. And that quenching time is a prominent reason for that. Below that, oxygen starts to become more monatomic, becomes molecular. And so below about 60 miles, the molecular oxygen and molecular nitrogen contribute to the aurora. What happens with nitrogen? I think I have the slide on here on that. Okay, the atoms that are involved, the energy, just a minute, and the altitude. All these things are factors as to which species is going to dominate for the color. There's also color mixing that it can occur. You have red and green mix, and you get, I don't know what you get. If you're a good color person, tell me what red and green mix to give you. Probably a mess. If I was mixing paint, that's what I get. The sensitivity of the human eye is also a factor in what color you're seeing, because our eyes are most sensitive to green light by design. Here's a few examples. Here's the emission spectrum. What'd you say?
Someone already said it, red plus green gives you yellow.
Oh, I guess that's probably a good answer. There's a difference between the additive spectrum and the subtractive spectrum. And I'm assuming that we're using an additive spectrum to get yellow. So that may be the case. But anyway, there's the lines that I was showing. There's actually 2 lines there very close to each other at 630. And I think it's the larger one that has the 110 second half-life. And the green line in oxygen is 0.74 seconds. Well, I told you earlier, I was planning to bring up a spectrum tube, and I had a spectrum tube with oxygen, and I put it on my power supply, and I couldn't I got one little taste that I thought I'm seeing the green line okay, and I was really having trouble. I thought, well, I can't show it to a group, you won't see it. So I went out, I bought another oxygen tube, same story. Then I started doing a little investigation, and everybody says the oxygen tube doesn't really show up very well. And I think the reason has to do with this quenching phenomena. Now, Mother Nature basically separates those ions for us because of the thin air and so forth. So we get, and there are ways, and I've read this about some researchers that can get a very bright line of oxygen. So under specific conditions in a lab, they can create that green line quite nicely. But a spectral tube is not a good place to do it. So I have learned that lesson again the hard way. There's a lot of lines that are close to each other in molecular nitrogen. I did not talk about molecular orbitals, and that's outside the scope of what we're talking about tonight. But molecular orbitals have a lot of different energy states, and so the transitions in nitrogen are much closer together, so we sometimes talk about that as a band spectrum. So now let's go from what we just saw to some of the pictures. This is a type A aurora where atomic oxygen and altitude account for the color. Notice there's red on top, green on the bottom. Never the other way around. Here's another one, type A, red over green. And this was taken over Missouri on a flight. Now, another thing that you might find out, if you ever are somewhere in the US or somewhere where you can see an aurora, and it's really an energetic one, watch again in 27 days. Anybody have a clue why 27 days?
Sun's rotation period.
No, moon doesn't have anything to do with it. It's a rotation of the sun. Sun takes about 27, remember it's a gaseous star, so it rotates not in one fixed amount of time. It depends on whether it's the equator or the poles and so forth. But about 27 days after a really intense aurora, you may see another one, because if there's a coronal mass ejection or a hole or whatever on the sun, it's going to repeat in about 27 days. That's the reason. So we had one this year, September 14th. There was a hole that came across that gave us a really great aurora. So if you want, and I don't know if anybody's going to try me, but if you wanted to look outside on October 11th, that'd be 27 days of this year. So look outside, it repeats in 27 days. Here's another type A aurora taken from the ISS. Notice the red over green. This is one I took, and I think that was near Fairbanks, Alaska. I believe I took that one. Maybe I didn't. Oh, I didn't. No, I'm sorry. I have that. I have taken some that look a little bit like that, but that's not mine. But what's interesting here is look at the bottom edge of it. There's a pink edge. That pink edge is telling me that it's probably, and this is my interpretation of it, that it's probably molecular nitrogen creating that pink edge. Here's another, this one's type B. It's green with a red on the lower edges. That very slight red on the lower edges is, again, probably molecular nitrogen. It's not atomic oxygen, which would be if it was red over green. There's a little bit of hint of yellow, and I think Alan correctly points out red and green create yellow, so there's a bit of a hint of yellow in here. This is an all green. This is a picture I took at Chena Hot Springs. And so that's a type C aurora. The person that typed these it was basically Neil Davis from the University of Fairbanks, and they do the aurora studies there, and they list these different types. Here's the same night on a road leading out of Chena Hot Springs where there's snow, and I just took a flashlight and kind of lit up the road on the right. And here on the left was in Norway, where the moon had been pretty full. It was, I don't remember what phase it was in. My picture doesn't really show it. It was too well burned out. But you can see the aurora, a bright aurora with a bright moon. It's not your preferred way to do it, just like looking at any star field, you prefer to be in a dark sky. But so if you have a choice and you can go with no moon, that's best. This is a type red, all red, a type D from a high altitude, and it's atomic oxygen. There's some other streaks in there that I don't think are atomic oxygen. I'm not sure why. Here's another one. This one I did not take. Now, there's also type E that he lists, fast-moving type C. Some of these I've tried to classify when I see them, and I could be wrong, but I believe this was the type E, fast-moving type C. Auroras are classified also by brightness with an international brightness scale, which goes from 0 to 5. 5 is the brightest. So here's a aurora with an early evening, and there's some local nitrogen molecules that emit the blue-violet light at the top. So that's by resonance scattering, and sunlight can contribute to the aurora because remember, the auroras are much, much higher than we are down on the ground.
How fast do they move?
They can change in a matter of seconds. You're watching and it's just moving. It's a moving curve. Have you seen them move faster than that, Dave?
No, I agree, that just, you can see them move in just a couple of seconds.
Yeah, it's pretty fast, but it's not dramatically fast. But they change. If you're taking a picture, you could take one every couple of seconds, and it'll be a little bit different for sure. If it's a nice active aurora. When I've seen it in the States at Grass Valley or North Dakota, they don't change very rapidly. They do change, but they're not rapid changes. Here's another one that was photobombed. It was a space photo of the day for June of this year. And this was photobombed by a meteorite, I believe. And that was in, like I say, space photo of the day. There's also something I have never seen, and I know Dave lived in Alaska, so he can comment if he did. I've never seen a blue aurora, but there's one that's a blue aurora. This one was taken in May of 2019. I incorrectly wrote on my notes, by the way, and if you read it, I incorrectly said that it was taken in 29,019, and I'm pretty sure it was 2019. Blue auroras are sometimes associated with thermal phenomena, and that's called a STEVE, strong thermal emission velocity enhancement is what STEVE stands. Somebody took the word STEVE and tried to fit some words to it, but that's what they came up with. But there is occasionally a blue aurora that can reach, it's very intense, does have very intense. Oh, by the way, I'm going to ask you, Dave, have you seen a blue aurora?
No.
Okay, I think they're very rare, I gather. I have not seen one. This, though, is a picture I took near Fairbanks. And this next photo is the green blobs are patches that'll pulse. And again, they're very unique. I did not take it. I wish I had, or I wish I'd even seen it. But this aurora basically was associated with protons. So it was called a proton aurora, obviously. And they sometimes pulse. This is a different item, not a aurora at all. It's called a stable aurora red. And it's basically a misnomer of that word. It's not an aurora. It's basically linked to the ring current in high altitudes, and it's associated with geomagnetic storms. So if you hear the words stable aurora arc, recall that it's not really an aurora. And here's a stable aurora arc shown, taken again. I don't know where this one was taken. I found it online, and I did not get a reference point, but it shows the arc nature of that.
You're saying that's a ring current?
Yeah, it's from the ring current.
From the Van Allen belt?
Well, the ring current is outside the Van Allen belt, but it's only a little bit outside. So I guess, I'm not sure they're considered part of the Van Allen belt. I think they're outside the Van Allen belt. That's my understanding. This basically is, the other thing people do with auroras, they sometimes describe them based on certain phenomena you're seeing, whether it's a veil or an arc or whatever. So these are patches and veils. And again, I did not take these. I'll give credit where credit is due if I see the person that took the picture. I took this one in Norway, and there's rays here. Again, there's a little hint that I discovered. I didn't notice it when I was watching the aurora, but there's a hint of red on the lower edge, which again would be molecular nitrogen. And this is an overhead corona aurora. I have seen a corona aurora. I did not see this particular one, and I didn't get a good picture of a corona aurora myself. But corona aurora occurs when you're directly under the intense part of the aurora oval. And finally, here's another corona aurora. A rayed drapery in the form of a spiral. Again, I did not take this one. I don't know who did. This one I did take, and I think it's the same form. I took this in Norway. This was taken from shipboard, and you can see the reflection in the water taken from shipboard here on the back. And this was taken on the Norway ferry that you go. We went from Trondheim, which is far, far north of Norway, and down the Norway coast, in and out of the various fjords. It's a wonderful trip. I loved it. And if you do go on that, if you ever go on the Norway ferry, I recommend getting a room in the back corner of the boat. That's where we were, and it was the perfect room. I had the best room in the house for that one. Oops.
The landscapes and the trees, mountains, I mean, this is just not, it almost looks Photoshopped.
No, it was not Photoshop. Mine,
They look
I don't,
like Dave Wesselman's photos of
yeah.
stars and land.
No, these are what we saw. This is not, now some of them, I won't say they aren't Photoshopped. In fact, I would say some of them are Photoshopped for sure, but mine were not. What I do with my photos is I'll enhance it, put some more, usually what I'll do is do something with contrast, brightness, the color saturation occasionally. A lot of these you don't really need to. The color comes through, yeah.
Landscape alongside.
This particular picture is another one that I had a long story. Read my story in there, but I have to tell you, I'll give you a hint if you don't read it. The hint is I took this in my pajamas with about 20 below zero, and I was freezing my buns off. So you can read the story about it, but it changed rapidly. I did have a robot too. This is a photo somebody took. I just thought it was interesting because they got a picture of a little cabin. And I think if you go and you want to take pictures, what a great idea. I'm going to try to, if I go again, which I hope to do this spring, I'd like to find a cabin somewhere. But I have to run this past my wife, and I don't know if she's going to go for this one or not, but we'll try. The picture here, I was in Fairbanks the last night we were out, and I looked out the hotel window, and the aurora was going on, and that the motel or hotel, whatever it was lighting up the tree in the foreground. And I thought, what a neat ray. And I thought, nice story. So here it is. Now, this is a picture that, oh, I'm sorry. I put Todd on there. I thought for a minute it was my name. My son took, and this was taken last year in November when we were up at Fairbanks. And that was just taken with a cell phone. When I got home, I said, well, I can improve that with a little saturation. So here's my improvement. So I went into Photoshop, and that's how I changed it in Photoshop. So you see a lot of that being done, but that just kind of shows you what you get off the camera versus whatever. Sad part is I didn't have pictures from that particular trip because my cameras got stolen. So this is retouched, and I did say it. There's a diffuse aurora without features. That's another one of the forms. And this one, we're talking about auroras on other planets. Never before had anyone observed that aurora could happen on Mars. And this was actually taken with the Mars rover, and it's a green aurora. So what does that tell you? There's some ionized oxygen on Mars, yes, in the atmosphere. It's very, very thin, and there's no magnetic field. And Neil Davis, in his excellent book, said it is not possible to have an aurora on Mars, and the rover found one. So this was a first for everybody. It's the first time anybody had seen it, March 24, 2024. One of the things I want to mention about this particular aurora is if you look up Mars aurora online, you will find some wonderful pictures with streaks and rays and all kinds of stuff. And I said, that's been Photoshopped because there's no magnetic field on Mars. It can't have rays. That's Photoshop. But who would think that you go online and find a fake picture? I guess everybody. The Martian aurora, there's mysterious objects called brown dwarfs that are sometimes called failed stars. The James Webb Telescope picture of a failed star showed that there were auroras on brown dwarfs. And this is an artist idea of what it might look like. So I did not, this is not a photograph, it's an artist. But here's another one. It's a rogue planet. Now, what's the difference between a rogue planet and a brown dwarf? Not much. Rogue planets are smaller, and they can have auroras. And what happened is, this was written up just this year, 2025, about a rogue planet that that's the James Webb Space Telescope, had taken, and they said absolutely there was an aurora there. And the planet number is SIMP-0136, is about 20 light years away. And the paper about this was just written last week, September 26th. And so it's in the AAAS, that's American Association of Applied Science. And they wrote a paper on it. And I wrote to the author and I said, how can a rogue planet that does not have a sun anywhere have an aurora? What's the mechanism? Where's the solar wind coming from? And he wrote back an email, which is reprinted on your notes. And it basically said, that's a good question. And we're having an argument amongst the authors as to what it could be. And essentially, he gave me 3 possible causes of how this could happen. I think the most likely one is the Jupiter theory, and I'll tell you about the Jupiter theory in a second. But you'll have to wait. This is Saturn with an aurora taken from, I think it was Cassini Space Division. That was from NASA. So Saturn can have auroras as Earth does. This was taken on 2 different wavelengths. As you know, the James Webb Space Telescope is primarily infrared, so it's not going to necessarily have auroras that look like what you see in a regular camera. Let's see, this is Jupiter, and this is interesting. Jupiter has alvenic activity again that they credited, but it's really Jupiter's moon Io that contributes to this aurora. As you know, Io is a weird planet with all kinds of volcanic activity going on. And the volcanic activity is ionized. And that ionized volcanic activity goes over to Jupiter and is the primary driver of Jupiter's aurora. So that's kind of an interesting story. And the author of the rogue planet idea thinks there may be a unseen moon on that rogue planet that is contributing in the manner of Io on Jupiter. So that was the interesting part of that story to me. Okay. Guess what? We're almost done. Yay! Let's see if I can. I'm having. Oh, here we go. All right, what's this one? Oh, this is the quiz. This is okay. We're at the quiz point. See what you learned tonight. So, where do northern lights go if they've been bad? They go to prism. That's corny, I know. Okay, sorry. All right, next quiz question. See how you do with this one. What should you do if you're lost in an Icelandic forest? Yeah, exactly. Stand up. Their forests are pretty short. And why are Van Allen belts important? They hold up Van Allen's pants. All right, so I don't know how you did on the quiz. I didn't hear a lot of correct answers. So you may have failed my class on auroras. I have at the back of your PowerPoint on the thumb drive a list of recommended books. I have read these and I have my little description of it. My very favorite is the first one each time, The Earth's Magnetic Field by Lowry, and I brought that with me so you can thumb through it and see it. He talks a lot about stuff that other authors don't, so I think it's a new book also. It was published in 2023. On the aurora, on the magnetic field, there's introduction to Alphean waves. This is actually this is a chapter I read. I admit that I only read the chapter because the book's pretty expensive. You can get chapter 1 as a free download from Wiley, and that chapter really talks a lot about Alphean waves. And something went wrong here on my. Oh, okay. I think this is probably the right link, so you might be able to use that link and get to that chapter. Now, as far as the aurora is concerned, my favorite book is The Aurora's Watcher's Handbook by Neil Davis. It's old, and therefore it's dated. He's got things like how to photograph it, and the best thing he can do is come up with an ISO of like 2000, which was really high in 1992. Today, we routinely get 20,000 ISO and more. So the photography section is dated. I wouldn't, and it's all on film. And nobody uses film anymore, except a few people, but I mean, almost nobody. A section on photography is out of date. The author is now deceased, but I listened to a lecture from him in Alaska. He was a great guy. It was, he did a talk for our 2001 trip with Astronomy Magazine. There's a few other things here. There's websites that I like. And for part 1, I diagrammed it for part 1 and part 2. So if there's a particular thing you were interested in learning about, it's all on there. And that's basically it. So thank you.